Hello students, welcome back. So in the previous class I had introduced you to the concept of isoparametric elements which are defined from -1 to +1, and we had derived some shape functions, and let us continue this concept for higher order elements. We have seen the derivation for 4 node quadrilateral element. We have derived the shape functions using both the LaGrange method and then the generalized coordinate method, and we saw that we got the same functions. Now let us go on to the much higher order element, say a 9 node LaGrange element. This is a pure LaGrange element because we have the same number of nodes along each line, whether along the xi direction or along eta direction, and node 1 is in the positive quadrant, node 2 is in the second quadrant, node 3 is in the third, node 4 is in the fourth quadrant, and so on. And by looking at our 3 node bar element, we can say that our shape function at this point xi of +1 is xi times xi plus 1 by 2, and the shape function at -1 is xi times xi minus 1 by 2. At this point, at the mid side point at xi of 0, 1 minus xi square. Then in the eta direction, eta times eta plus 1 by 2, 1 minus eta square, and this. And the advantage with the Lagrange method is we get the shape function separately in the two directions, xi and eta directions, and then take a product to get our shape function. So the n1 will be the product of this and this. So our the n1 is xi eta times 1 plus xi 1 plus eta by 4, whereas n9 is just simply the product of this and this, 1 minus xi square 1 minus eta square, and then similarly all the other at all the other nodes. Okay, and we can get the same shape functions even by using the generalized coordinate method. The polynomial for the 9 node quadrilateral is alpha naught plus alpha 1 xi plus alpha 2 eta plus alpha 3 xi square plus alpha 4 xi eta, and so on. Okay, and we can derive the shape functions, and we will see that the shape function that we get from the generalized coordinate method are exactly the same as what we get from the Lagrange method. And the advantage with the serendipity method of correction is we can incorporate the elements with which are not exactly Lagrange elements, like with any variable number of nodes. Say for example, we can think of a quadratic element with 5 nodes. So let us say we have a 5th node here, or we can have a 6th node, like 6 node elements 1, 2, 3, 4, 5, 6, or 7, 5, 6, 7, or 8 node element 5, 6, 7, 8, and these are not Lagrange elements, these are called as serendipity elements. And for deriving the shape functions for this, we need a separate procedure, and so let us see what that is. So in fact this 8 node element is very popular in finite element analysis because it is very powerful, and we get a good accurate result, and not only in the elastic analysis but also in the elastic plastic analysis. So for the 5 node element, we can start with the shape functions for the 4 node element 1, 2, 3, 4, and then introduce the 5th node and do the correction. Okay, and so we can actually directly write our these shape functions based on the Lagrange procedure like this. Okay, and if you see at node 1, our the shape function for 4 node element is 1 plus xi 1 plus eta by 4, and at node 2 1 minus xi times 1 plus eta by 4, and at node 3 1 minus xi times 1 minus eta by 4, and node 4 1 plus xi 1 minus eta by 4. Okay, now we have introduced the fifth node at this point, and that is 1 minus xi square, because this is the middle node along the xi direction when you have 3 nodes, and then in the eta direction this is at eta of plus 1, and there are only 2 nodes along the eta direction. So, this could be written as 1 plus eta by 2. But if you introduce this node, the problem is if you substitute eta of 0 and xi of 1, we have a problem. We do not get 0, because our object is the shape functions should have value of 1 at their own node and 0 at all the other nodes. So, when you had a 4 node element, that was easy, like if you substitute xi of the eta of 1, you get 1, but if you substitute xi of minus 1 or eta of minus 1, you will get 0, and so on. Okay. But when you introduce this node at node 5, then this is not 0, but it is half. So, to make n1 and n2 as 0 at this point, I can say n1 at fifth node is n1 for the 4 node element minus n5 by 2, and n2 for 5 node element is n2 for the 4 node element minus n5 by 2. And these two shape functions 3 and 4 need not be corrected, because if we evaluate these two along this line where eta is plus 1, they will automatically become 0. Like for example, if you substitute a eta of 1, n3 is 0 and n4 is 0. Okay. So, just by correcting these two shape functions, we can get the shape functions for the 5 node serendipity element, and then if you sum up all the shape functions, you get 1, that is the corrected shape functions n1 and n2 for the 5 node element plus n5 plus n3 and n4, you will get 1. That I have not done here, but you can do it yourself. Okay. And now let us introduce the 6th node. Okay, let us start with the 4 node element. These are the basic shape functions for a 4 node quadrilateral, and n5 is 1 minus xi square times 1 plus eta by 2, and n6 is 1 minus xi by 2 times 1 minus eta square, because this is at xi of minus 1, and on the right hand side the other one is xi of plus 1. Okay. So, in the eta direction there are 3 nodes, so we can write like this, and if we evaluate n1 and n2, they are half here and they are also half here. Then n3 is also, if you evaluate n3 for the 4 node element here, you will get half, and n3 along this line is 0, and n4 is 0 if you evaluate along this line or along this line. So, the n4 does not require any correction, and n1 requires a correction because of node 5, whereas n2 requires a correction for node 5 and node 6, and n3 requires a correction for node 6. So, we can write n1 for the 6 node element as n1 for the 4 node element minus n5 by 2, and n2 for the 6 node element is n24, that is n2 for the 4 node element minus n5 by 2 minus n6 by 2, and n3 for the 6 node element is n3 for the 4 node element minus n6 by 2. and N4 for the 6 node element is exactly the same as N4 for the 4 node element, and the sum total of all the shape functions is equal to 1, because that we require for unique for the uniqueness in the mapping. Okay, that we will see later why we need the sum total of all the shape functions as 1. Okay, and we can introduce the 7th node, and now our N1 is corrected because of N5, and N2 is corrected because of node 5 and 6, and N3 is corrected because of nodes 6 and 7, and N4 is corrected only because of 7. Okay, and that correction is see, the correction for N1 is N1 7 is N1 4 minus N5 by 2, that is the N1 for 7 node quadrilateral element is N1 for the 4 node element minus N5 by 2, N2 for the 7 node element is N2 minus for the 4 node element minus N5 by 2 minus N6 by 2. Similarly, we can do for all the other nodes, and we can do this just by observation. We do not really need to derive them, and I forgot to ask you one question. See, for the 5 node element we got these shape functions, but if you assume a polynomial and derive using the generalized coordinate method, you will see that you will not get the same shape functions, because earlier we got the same shape functions whether we used LaGrange method or the generalized coordinate method, because we were applying the procedure for a purely Lagrange element, but these elements, these transition elements are not Lagrange elements, these are something else. So, we have to use only the method that we are using, the serendipity method, and basically all these elements with variable number of nodes, so these are called as transition elements. 7, and then 8 node quadrilateral is actually it is a very powerful element wherein all the 4 nodes N1, N2, N3, N4 they get corrected. So, N4 for the 8 node element is N4 for the 4 node element minus N7 by 2 minus N8 by 2 and so on. Okay. N1 8 is N1 for the 4 node element minus N5 by 2 minus N8 by 2 and so on. Okay. So, these directly by observation we can write, and the main advantage here is we can easily program them, and these elements are formulated in terms of -1 to +1. So, if it was x1 to x2, we do not know how much correction we need to apply, because we cannot do this type of simple calculations. So, these the 2 elements, the 4 node quadrilateral and 9 node quadrilateral, they are pure Lagrange elements, and the others with 5 nodes, 7 nodes, 6 nodes, 8 nodes, these are all called as transition elements, and they are used in adaptive meshing. Sometimes or some programs they give you an option for adaptive meshing, so that you get more closer mesh where you have say some very high strain variation or some point is of interest for you, and we can use this variable number of node elements for transition from one type of element to the other type of element. And so, this table summarizes your different shape functions. So, N1, N2, N3, N4, these are the basic elements, and N5, N6, N7, N8, and these columns. So, if you introduce N5, you correct N1, and then N2, okay. And if you introduce node 6, you correct n2 and n3, and with node 7 we correct n3 and n4, and so on. Like with if you introduce 8th node, we correct 1 and 4. Okay, and then with the 9th node we have correction for all the other 8 nodes. These are the corrections that we need to apply, and this table tells you what to do, and it's very easy to program to change the number of nodes from 4 to 9, and this is what is done in most finite element programs. I will show you one program like later on how this is done to change the number of nodes from 4 to 9 and adapt any number of nodes that we have. Okay. So now we have developed our mapping and shape functions in terms of xi and eta instead of the Cartesian coordinates x and y, and so we cannot directly determine our Cartesian derivatives of n, dou n by dou x and dou n by dou y, and unless you derive them, we will not be able to form the B matrix, because the B matrix is required for forming our stiffness matrix or for calculating the equivalent loads due to your initial stresses and so on. Okay, and as m and n, both the mapping and shape functions, they are written in terms of xi and eta, which are in turn related to Cartesian coordinates x and y. Right? There is a relation, certain relation between xi eta and xy. Okay? So we can use the chain rule of partial differentiation to obtain the required derivatives. Okay? And what we do is we can write our dou n by dou xi, because our xi is related to both x and y. So I can write dou n by dou xi as dou n by dou x times dou x by dou xi plus dou n by dou y times dou y by dou xi, because this is a chain rule of differentiation, because xi is dependent on both x and y. Similarly, the dou n by dou eta I can write as dou n by dou x times dou x by dou eta plus dou n by dou y by dou eta. And here if you look at these two equations, dou n by dou xi we can directly evaluate, because our shape functions are formulated in terms of xi and eta, and our dou x by dou xi and dou y by dou xi also we can evaluate, because our mapping functions are formulated in terms of xi and eta, and our x is sigma of mi xi. Okay. So our x is sigma of mi xi and y is sigma mi yi. So we can write dou x by dou xi as dou m by dou xi and so on. Okay. So here we know the left hand side, and then we know the dou x by dou xi, dou x by dou eta, dou y by dou xi, dou y by dou eta and so on. Okay. And so we can actually write this in matrix form like this: dou n by dou xi, dou n by dou eta, and then dou x by dou xi, dou y by dou xi, dou x by dou eta, dou y by dou eta multiplied by dou n by dou x, dou n by dou y. And here we know the left hand side, because our shape functions are written in terms of xi and eta, so we can determine these. Then this bracket is a very important quantity that we evaluate. This is called as a Jacobian matrix, that is consisting of the derivatives of x and y with respect to xi and eta. So by inverting this matrix, we can get dou n by dou x and dou n by dou y. Right, and our inverse of the Jacobian matrix is 1 by determinant of the Jacobian times dou y by dou eta minus dou y by dou xi minus dou x by dou eta, dou x by dou xi. Okay. And the determinant of this Jacobian matrix is dou x by dou xi times dou y by dou eta minus dou x by dou eta times dou y by dou xi. Okay. So, this is also very important quantity. The Jacobian should be positive definite for unique mapping, because previously we said some things like our all the internal angles should be less than 180 degrees, and then they should not be yeah, and then the intermediate point should be within the middle third and so on, and the more check is done by this Jacobian matrix that we derive. Okay. And the determinant of the Jacobian matrix will be positive definite only when element nodes are in anti-clockwise direction. We have to number all the nodes in the anti-clockwise direction, and it has to be positive definite because it represents the area of the element to some scale. Okay. And then if it is positive definite, that means that we have unique mapping, and the shape function derivatives with respect to Cartesian coordinates now can be written like this: dou n by dou x, dou n by dou y, in terms of all the other parameters. Okay. And all the quantities on the right hand side we can actually write out in analytical form when we are programming. It's very simple to program. Okay. And now we got a relation to get your shape function derivatives with respect to Cartesian coordinates x and y, and now we are dealing with integration in Cartesian space, integral of x and y, but now we have with the mapping we are working in terms of -1 to +1. So, how do we do that, and how do we establish the relation between the Cartesian space and then the isoparametric space, isoparametric or natural space. Okay. So, let us take an infinitesimal element dA of dx dy in the Cartesian space, and then in the isoparametric space dxi d eta. And now we want to establish a relation or the scale factor between dx dy and dxi d eta, right? And how do we do that? So, for that we can go back to our vector calculus, and let us imagine these two lines PQ and PR as two vectors, and along this line your eta is constant, right, because we are moving along xi, and then along this line your xi is constant. Okay. And in general our vectors are written like dx we can write in terms of dou x by dou xi dxi plus dou x by dou eta d eta. Because our x is a function of both xi and eta, I can write it like this: dou x by dou xi dxi plus dou x by dou eta d eta, and dy also can be written as dou y by dou xi dxi plus dou y by dou eta d eta, because both x and y are related to xi and eta. Okay. And so, along this line your eta is constant, that means d eta is 0. So, we do not have the dou x by dou eta terms like and dou y by dou eta terms, because d eta is 0. So, we can write this length as dou x by dou xi times dxi, and this as dou y by dou xi dxi. Okay. And the PQ is this is actually it is a vector dou x by dou xi dxi I plus dou y by dou xi dxi in the j direction. So we can write the vector is in general written as dxi plus dyj, and along this pq, eta is constant. So I can write the pq vector as dou x by dou xi times dxi I plus dou y by dou xi dxi j. Okay, and this is a vector, and similarly along the vector pr, your xi is constant. So dxi is 0. So we can write dxi plus dyj as dou x by dou eta d eta I plus dou y by dou eta d eta j. Okay. And in the vector calculus, the area is a cross product. So we have developed two vectors pq and pr, and if you take a cross product, we will get the area. Okay. So your and then when we are doing the cross product, I cross j is k, I cross I is 0, j cross j is 0, and j cross I is minus k, right. So if you do this cross product, we will get dou x by dou xi dxi dou y by dou eta d eta k, positive k, minus this multiplied by k. So our this is our dA, that is dx dy, and that is equal to, this is actually determinant of the Jacobian matrix multiplied by dxi d eta. So now we can say dx dy is nothing but the determinant of the Jacobian matrix multiplied by dxi d eta. So we can write in general integral x1 x2 integral y1 y2 dx dy as integral of -1 to +1 integral -1 to +1 determinant of the Jacobian matrix J dxi d eta. And so actually for the 9 node element, this is what we have done. We took these 9 terms, 1 xi eta, xi square, xi eta, eta square, xi square eta, xi eta square, and xi square eta square. We have the 9 terms for the 9 node Lagrange element. Okay. So now let us apply this, if you want to do any calculations, we can do this, and then how do we do this numerically? So we can write in a summation form for doing the numerical calculations. I can evaluate the xi and eta at some specific locations, and then do the calculations. That is what we are going to do. Okay. Let us say that we are given a 4 node quadrilateral or a rectangle with these coordinates, and then we are interested in finding the area of this element, and the area of the element we can get as the okay. So this is the area of the element, integral dx dy integrated from x1 to x2 y1 to y2 is determinant of the Jacobian matrix J dxi d eta integrated from -1 to +1, and this in a numerical form we can write it in the summation form like this. We can write the area as the summation over xi, summation over eta, determinant of the Jacobian matrix wi wj, where the weight factors in the xi direction and eta direction. So our shape functions at these 4 nodes are like this: 1 plus xi, 1 plus eta by 4, 1 minus xi, 1 plus eta by 4, and so on. Dou n by dou xi, dou n by dou eta. These are just simple derivatives with respect to xi and eta. And now we can calculate dou x by dou xi as dou n by dou xi times xi, right? And we have 4 x values: x1 is 15, x2 is 5, x3 is 5, and x4 is 15. Okay. So dou n1 by dou xi times x1 plus dou n2 by dou xi x2 plus dou n3 by dou xi x3 plus dou n4 by dou xi times x4. And these are the different derivatives and these are the coordinates. And if you do the calculation, it is a constant value 5. It's not a function of xi or eta. Then similarly dou x by dou eta, if you calculate, it's coming out as 0. So why does it why did we get this type of answer? Dou x by dou xi is an absolute constant, and dou x by dou eta is also an absolute constant, but it's 0. Why? So actually when you look at this, the shape of the element, a rectangle, your xi and eta are coinciding with x and y. So xi is coinciding with x coordinate and eta is coinciding with the y coordinate. So as you are moving along x axis, your eta is a remaining constant. Similarly, if you are moving along y, your xi is a remaining constant. Okay? Or as you are moving along xi, your y is constant, and as you are moving along x, your eta is constant. So our dou x by dou eta, the variation of x along eta direction is 0. That is what we can see from this figure itself. And then similarly dou y by dou xi, we get it as equal to 0. That is the variation of y along xi direction. That is constant because this element itself is a rectangular shaped element. And dou y by dou eta, that is the variation of y with respect to eta, that's coming out as 4. So this dou x by dou xi is 5 and dou y by dou eta is 4, and this 5 is coming from the half length. See, the length along the x axis is 15 minus 5, that is 10, and 10 divided by 2 is 5. Okay? And the length along the y axis is 15 minus 7, that is 8, divided by 2 is 4. So now the area of this element can be written as double summation over xi and eta mod j multiplied by wi wj, where wi wj are the scale factors, and we can just simply use a one point integration for doing this calculation, because the polynomial is anyway a constant. Like this we don't see any polynomial terms in the dou x by dou xi or dou x by dou eta and so on. 5 0 0 4. Okay. So our determinant of the Jacobian matrix is 20, and the area of element is j multiplied by w1, that is 2, times w1, that is 2, that is 80. So that's exactly equal to the area of this element, 10 times 8. Okay. And with just one point integration, we can get the area of this element, because in fact the polynomial order is 0, there is no variation. Okay. So now let us take a distorted shape. Let us take the same 4 nodes 1 2 3 4 and assign some properties so that you have a distorted shape like this. Now we see that dou x by dou xi, dou x by dou eta, they are not 0, they are varying in as a function of eta and xi. Similarly dou y by dou xi, dou y by dou eta, they are functions of xi because they are varying. And actually here how many integration points do we require? So our dou x by dou xi is only eta, that's a first order polynomial, and dou y by dou eta is also a first order polynomial, because it's 4.25 plus 0.25 xi and so on. Okay. So, this product, the determinant of the Jacobian matrix, is a first order polynomial. So, that means that if you use one point integration, you should get the exact result. And so, by one point integration, we get 62.5, and the area of this element, actually I have calculated separately by splitting this into two triangles, and then we have a formula for estimating the area of the triangle as the determinant of the coordinate matrix 1 x1 1 y1 1 x2 y2 1 x3 y3. The determinant of that matrix will give you the area of the element. Okay. And by doing that procedure, we got the area of this element as 62.5. Okay. And let us see if you apply higher order of integration like 2 by 2 or 3 by 3, whether you get any different answer. But of course, it is a tedious process. With 2 by 2 integration, our sampling point locations are minus 1 by root 3, minus 1 by root 3, and the weight factor is 1, and minus 1 by root 3 plus 1 by root 3, and so on. Okay. And so, if you substitute the various values, you will actually get a very complicated equation, and then on top of that, we have to substitute xi and eta values at 4 points, because it is a 2 by 2 integration, and we will get a long equation. And if you solve this long equation without rounding off any numbers or writing out intermediate values, we will see that this is 62.5. Okay. And we can apply even the 3-point integration, but then we will end up with the same value. And if you use a 4-point integration, we are evaluating all the quantities 4 times. And if you use a 3-point integration, we need to do 9 evaluations. See, for something that could have done with just 1-point integration, if you use a higher order of integration, your computational effort is more, but the result is not going to change. Okay. So, this is how we can do these computations, and in this class we have got a relation between the Cartesian space and then the natural space, and then we found a way of determining the Cartesian derivatives of the shape functions dou n by dou x and dou n by dou y. And now we are ready for doing all the finite element calculations using our isoparametric elements. Okay, that we will do from next class. So, if you have any questions, please send emails to this address profkrg@gmail.com, and before you come for the next class, please do try to understand all the previous lectures so that it becomes more easy. Okay. So, thank you very much.